Hi guys, unfortunately this video isn't about the kind of transformers you just saw. Yes, we would have liked it too if this video was about the Autobots and Decepticons, but that's a video for some other time. In this video, we're discussing the transformers that we usually hear about when we're talking about the change in voltage in electrical appliances. Throughout this video, we'll be looking into the setup of a transformer, its working principle, back EMF and other energy issues in a transformer, and also the application of transformers in human life, such as in a transmission line. Please bear with us.
Function of transformer. The potential difference from the electrical supply in our homes is 240 volts. This voltage is not suitable for certain electrical equipment. For example, the television tube requires a potential difference of 15 kV, whereas a radio requires a potential difference of only 12 V. Therefore, it is necessary to raise the electrical voltage from 240 V to 15 kV and to lower the voltage from 240 V to 12 V so that the television and radio can function. The equipment used to raise or lower the potential difference of an alternating current supply is called a transformer. Transformers also play an important role in the transmission and distribution of electrical energy to the whole country. The transformer transfers electrical energy from one circuit to another through electromagnetic induction. Constructing a transformer. A simple transformer consists of two coils wound on a laminated iron core. The coil which is connected to the power supply, whose voltage is to be raised or lowered, is called the primary coil. The supply voltage is called the primary voltage, which is also known as input voltage, represented by the symbol Vp. The other coil which is connected to the electrical equipment or resistor is called the secondary coil. The voltage across the secondary coil is called the secondary voltage, which is also known as output voltage, represented by the symbol Vs. Principle of operation of transformer. The operating principle of a transformer is based on electromagnetic induction. The current from the electrical supply that is connected to the primary coil is a sinusoidal alternating current. That is, a current whose magnitude and direction vary continuously at a certain frequency. The alternating current produces a flux or magnetic field lines which link the primary coil and the secondary coil. The magnetic flux produced varies in magnitude and direction. The changing magnetic flux produces an induced EMF across the secondary coil. This induced EMF also varies in magnitude and direction. As a result, the secondary voltage is also a sinusoidal alternating current. If the secondary circuit is closed, a sinusoidal alternating current flows in the circuit with the same frequency as the electrical supply. It is very important that the primary coil must be connected to an alternating current supply and not to a steady direct current supply. This is because an induced EMF will not be produced in the secondary coil if a steady current is used. A steady direct current whose magnitude and direction is constant does not create a changing magnetic flux in the secondary coil.
The constantly changing current driven by the alternating voltage source induces a changing magnetic field in the core of the transformer. The magnetic field created by the alternating current in the primary coil generates the flux in the transformer core. The secondary coil converts the flux back into current flow and produces a voltage at the load or resistance in the secondary circuit.
There are two types of transformers, which is the step-up transformer and the step-down transformer. In a step-up transformer, the number of turns in the secondary coil is greater than the number of turns in the primary coil. A step-up transformer increases the voltage from the primary circuit into the secondary circuit. Conversely, in a step-down transformer, the number of turns in the primary coil is greater than the number of turns in the secondary coil. A step-down transformer decreases the input voltage to produce a lower output voltage. The formula used to calculate either the number of turns of coil or the voltage in the primary or secondary circuit is V secondary over V primary equals to T secondary over T primary. This formula simply states that the secondary voltage to primary voltage ratio is the same as the secondary coil to the primary coil turn ratio. Here's an example to show you guys on how to calculate the secondary voltage. First, as we can see, there are 20 turns in the primary coil, and the primary coil has a voltage of 120 volt, while the secondary coil has 10 turns, but its voltage is unknown. To calculate the secondary voltage, we divide 10 by 20 and then multiply it by 120, where 10 is the number of turns in the primary coil, and 20 is the number of turns in the secondary coil, while 120 is the voltage in the primary coil. In the end, we will find out that V secondary is 60 volt.
Efficiency of a transformer. The efficiency of a transformer is normally less than 100%, that is, the power of the output is less than the power of the input. A transformer transfers electrical energy from one circuit to another circuit by electromagnetic induction. In the process, a fraction of the electrical energy is lost as heat energy. The formula used to calculate the efficiency of a transformer is efficiency equals to useful output power PO over input power PI multiplied by 100%. The ideal transformer. If there is no loss of energy in a transformer, all the energy supplied to the primary coil will be transferred to the secondary coil. Such a transformer is known as an ideal transformer, which has an efficiency of 100%. In this circuit, the output power is equal to the input power, which means Vi of the secondary circuit is equal to the Vi of the primary circuit.
Before we start about what is back EMF, first let's have a background about how coil differs from a resistor. According to Ohm's law, V equals to IR. Therefore, with a resistor, if you stick a voltage V across a resistor R, the current is nearly instantaneously reaching the steady state. However, this is not the same for a coil, because when you apply a voltage to a coil, the current doesn't reach its steady state value immediately. Instead, the current in the coil will have to build up gradually. Here, self-induction occurs. Self-induction is the process of an induced EMF in the conductor itself when the current in the conductor changes. According to the Lenz's law, a changing magnetic field inside the coil will produce an EMF in the coil that opposes the change in current that is produced. Therefore, the direction of back EMF is always on the opposite to the direction of the current. In other words, the reason why it takes time for the current to build up to the maximum steady state value is because while the current is changing, there is a back EMF which reduces the net voltage on the coil. Eventually, as the current approaches the steady state value, the rate of change of current reduces, and so the voltage of the back EMF approaches zero. Consequently, the full applied voltage finally appears across the coil and the current approaches its maximum. The more turns in the coil, the bigger the back EMF, and the bigger will be the time delay to reach the maximum current. If instead you decrease the applied voltage on a coil that is already at a maximum state current, then for similar reasons, it takes time for the current to decrease. Just use the same Lenz's law argument but now for decreasing current and fields. And now, because of the large number of turns in a typical transformer, the back EMF will be almost as large as the applied voltage. So the net voltage across the primary coil will be very small. Hence, this is one of the main issues faced by transformers in our national grid network.
Other than back EMF, one of the energy issues in a transformer is actually energy loss. There are a few factors that cause this, the first one being the resistance of coil. A coil has electrical resistance. Energy is lost as heat energy in a coil because of the heating effect of current flowing in a conductor. The power loss is equal to I square R, where R is the resistance of the coil and I is the current flowing in the coil. And this problem can actually be minimized by using a thick copper wire to reduce the resistance of the coil. Next is the magnetization and reversal of magnetization of iron core. When current flows in the primary coil, the iron core is magnetized. When the current direction is reversed, the magnetization of the iron core is reversed. The energy required for the magnetization and its reversal is converted into heat energy in the iron core. And to minimize this energy loss, a soft iron core which can be magnetized and demagnetized easily is used to reduce the energy needed to bring about the magnetic reversal in the coil. And then is the eddy currents in iron core. So the core itself is a conductor. So the changing magnetic flux in the iron core induces currents in it. These circulating eddy currents generate heat in the iron core. To deal with this problem, the iron core is laminated or layered. It is made from thin, insulated sheet of iron which is insulated with enamel paint to increase the resistance to the flow of eddy currents. With less eddy currents, energy loss is reduced. Finally, is the leakage of magnetic flux. Electrical energy is lost when a fraction of the magnetic flux produced by the primary coil does not link with the secondary coil. As a result, there is a reduction in EMF induced in the secondary coil. To overcome this problem, the iron core should be a closed loop of iron with the secondary coil wound over the primary coil or placed very close to the primary coil along the same core.
One of the applications of the transformer is that it is actually used in the national grid network. This network is actually used to transmit electricity from one place to another. As you can see, the electrical energy generated in power stations are at a voltage of 25 kilovolts, and it is increased to 132 kilovolts with a step-up transformer before transmission. The electrical energy is transmitted at a high voltage to reduce energy loss as heat in the cables. Just before reaching the various consumers, the voltage is reduced. It is reduced with step-down transformers at substations to suitable voltages of the respective consumers as shown. So why do we use the national grid network? Firstly, it is because that it is much more cheaper and is way efficient. This is because that the energy loss is minimized by transmitting the current at high voltage. Secondly, it is because the energy distribution is way efficient compared to other ways of transmission. This is because that the generation and distribution of electrical energy can be controlled according to requirements. Lastly, the energy management of the national grid network is also much better. If there is a breakdown or interruption of a supply at a particular power station, the power can still be supplied by other stations through the national grid network to the affected area.
We've come to the end of this video. Before we end, let's just have a quick recap on what we've looked into. First, we saw what a transformer is. We learned that it is a device that uses mutual induction to change a given AC voltage into a larger or smaller AC voltage. We also looked at the setup of a transformer and its working principle. And then we looked at the types of transformers. There are two types, a step-up transformer that increases the input voltage and a step-down transformer that decreases the input voltage. Here we also looked at the formula to calculate either the number of turns or voltage in the primary or secondary circuit, which is V secondary over V primary equals to T secondary over T primary. After that, we went through the efficiency of a transformer and looked at the method of calculating it using the formula PO over PI multiplied by 100%. Following that, we saw what an ideal transformer is and learned that it has an efficiency of 100%. And then we looked at how self-induction in a coil causes back EMF and how back EMF reduces the net voltage in a circuit. Other than that, we looked at energy issues in a transformer. Here we looked at 4 main issues and also included modifications that can be done to a conventional transformer to reduce energy loss. To add on to these modifications, superconducting transformers which are capable of increasing energy transmission efficiency are also being used these days. This is due to the special features in the superconducting transformer, such as not requiring iron, thus making the transformer compact and light. Coming back to what we've covered in this video, we looked at the application of transformers in the national grid network. We learned that the voltage generated in the national grid network is increased to reduce current flowing through the cable as to minimize power loss, and also that the voltage is reduced before being supplied to different places. Finally, we looked at 3 main advantages of using the national grid network. That is all for this video today. We do not own all contents of the video, therefore all references are included in the description below. You may hit the like button or feel free to comment, but please do not subscribe to this channel as this is not an active channel in which videos are frequently uploaded. Thank you.